Now that we have defined the LU factorization of a matrix A, let's use that factorization to solve the system AXB. Normally, in previous videos, we solved this system by writing the augmented matrix AB, then carrying out some elimination. And this took us to another system where the matrix A became a matrix U and the vector B became some new vector C, for example. So instead of solving AX equals B, we solved UX equals C. Well, now that we have elimination introduced as matrix multiplication, or rather captured by L, we can write a relationship between the systems AX equals B and UX equals C in a precise manner. Remember that when we write A equals L times U, L takes us from U to A, which means that L inverse takes us, so L inverse takes us from A to U. That means that the elimination here I have written is actually multiplication by L inverse. In other words, I would have L inverse applied to A gives me U. L inverse applied to B gives me the vector C, which can equivalently be written as A equals L times U and B equals L times C. So the factorization on A gives us this new vector B, or gives us the relationship between B and C. So in other words, we would start with a rectangular system. So AX equals B is a rectangular system. And instead of this one rectangular system, we can solve two triangular systems. Those two triangular systems are UX equals C and LC equals B. U is upper triangular, L is lower triangular. UX equals C is back substitution, while LC equals B comes from forward elimination. All right, now that we have a short description of the system, let's go ahead and solve this on an example. So if we were just given the matrix A and asked to solve AX equals B with B given to be 1, 0, 0, 0, we wouldn't necessarily need to find the matrix L. That would be redundant, because what we would do is we would augment B to A, carry out the elimination on both A and the vector B, and finally end up with having U and C right away. But in this example, imagine we are already told that A factorizes in this matrix, factors in these two matrices, L and U. So we are given the matrices, and by the way, this is the same Pascal matrix from the previous video. And you see that L and U are really very, very similar. Without going into very formal definition of transpose matrices, L and U are transposes of each other, which means that the columns of L are the rows of U and vice versa. You could say the rows of L are the columns of U, the corresponding columns of U. So we call these matrices transposes of each other. We'll define that formally soon enough, but it's just to show that they're kind of essentially the same matrix, very, very similar. Now, okay, let's go back to applying our theory. So we have the system AX equals B, And this gives us two systems. That is what did I have? LC equals B and UX equals C. So I need to first find out what C is to be able to solve the system UX equals C, because I don't have C right now. Okay, so how am I going to do that? I don't want to do elimination yet again. I just want to write the system. So let me write here LC equals B. Now, what I'm writing here, take the matrix L and write the equations. So we have, from the first row of L, we have x1, and from B, we know x1 must equal 1. Then the second row says x1 plus x2, then x3 and x4 don't show up, must equal 0. Then we have x1 plus 2x2 plus x3 equals 0. And x1 plus 3x2 plus 3x3 plus x4 equals 0. So just again, this over here is the vector B, and the system that I'm writing over here comes from the matrix L, okay? So what you see here is, because the system is triangular, we can immediately solve. There is no need for elimination, so kind of forward substitution. From the first equation, x1 is just 1. Now I can replace that value in the second, third, and fourth equation. So I have a 1, 1, 1. Now you see, from the second equation, let's change colors. From the second equation, I know what is x2. x2 must equal -1. So then I can replace x2 in the third and fourth equation. So this is a -1 and this is a -1. Now, from the third equation, I can write what x3 must be. So x3 here equals, let's just calculate what we have. We have 1 minus 2, that's a -1, plus x3 must be 0. That means that x3 must equal 1. And perhaps my choice of yellow color was terrible, but bear with me. So x3 in the last equation equals a 1. And now let's go in the fourth equation. From there, we can figure out what x4 must be right away. So we have 1 minus 3 plus 3. Minus 3 and plus 3 kind of cancel out. So x4 must be equal, oh, my bad here. I wrote x's when in fact I should have written c's. Okay, we'll quickly correct that. But anyway, the value here must be a -1. And let's see my erasing skills here. Yeah, these should be c's over here. So I'll just correct over here. C and C, and please, in your notes, all of these need to be C's. So just correct that in your notes. Before I upload these ones, I'll have C's written. So these need to be C's because we're solving for C. So the vector C equals 1, -1, 1, -1. And now we need to use this C to solve UX equals C. So now I'm going to write the system UX equals C. You see here how LC equals B was forward elimination or forward substitution, not elimination. So we just needed, we were able to find C1 directly from the first equation, then C2 from the second, then C3 from the third, and C4 from the fourth. When we go into UX equals C, we're going to use back substitution because we will start from the last equation and go back to the first equation. I'm going to write the system with x's, and these really need to be x's. So from the first row of U, I have x1 plus x2 plus x3 plus x4 x4 equals C1, which is 1. Then I have x2 plus 2x3 plus 3x4 equals -1. And then I have x3 plus 3x4 equals 1. And the last one is x4 equals -1. Again, this matrix, the coefficients for x1, x2, and x3 come from the matrix U. These are exactly the same system. And then these answers come from the vector C. Now you see immediately we have solution. So we know what x4 must be. x4 is just -1, and I can replace -1 in the first, second, and third equation. So here I have -1, -1, -1. This allows me to find what x3 must be. So from here I have x3 equals, so we have x3 minus 3 equals 1, which means x3 must be 4. Now I will use, another color. 4, I will replace 4 in the first and second equations. So I have a 4 here and a 4 there. Going back to the previous equation, I can find x2. So what do we have? x2 plus 8 minus 3. So we have a 5 there. Take it to the other side. We have -5 minus 1, so that's a -6. I can replace -6 in the first equation. And what I have is right away x1 from here. So how much is x1? -6 plus 4 is -2. Minus 1 is -3. Take it to the other side, it becomes a 3 plus 1. That equals a 4. So the vector x is 4, -6, 4, -1. So you see, once you have the LU decomposition or the LU factorization of a matrix A, there is no more need to do elimination. Forward substitution allows us to find C from B, and backward substitution allows us to find X from C.